Hi, everyone. Welcome to Stream Processing Meetup. Thank you for joining us this evening. My name is Efe. I manage LinkedIn Kafka team. And my co-hosts today are Gary and David. Gary is a senior engineering manager in the stream processing group, and David manages LinkedIn Samza SRE team. We have 3 exciting talks for you today. Each session is going to be 35 minutes. And the first one is going to be about how LinkedIn cleans up unused metadata for its pub subsystem. This is a talk from LinkedIn. The second talk is about event streaming with Kafka using Azure Event Hubs. This is a talk from Microsoft. And the third talk is on change data capture with Flink SQL and Brooklin. And this is a talk from LinkedIn. Before we begin, I would like to share some frequently asked questions. The first question is, are the talks being recorded? Yes, they're being recorded. Our LinkedIn engineering channel on YouTube will post the recordings after the meetup. And the meetup event site will also have the link to the meetup once it is available. The second questions we frequently get is, I want to present, whom should I talk to? We have a couple of options here. You can either post a message on the meetup site, or you can send a LinkedIn message to one of the hosts of this event, including me, David, or Gary. Or you can send us an email and we will get back to you. How can I ask questions to the presenters? To ask questions, please use the Q&A tool on Zoom. This tool, you will notice, is located at the bottom of the Zoom window. And at the end of each talk, our presenters will take time to answer the questions. And depending on the time, they may cover some of the questions after the talks conclude. And with that, I will introduce our first speaker. And let me stop sharing. Our first speaker today is Hao. Hao is a self-motivated and creative engineer. He has been working on large-scale services and infrastructure for many years, and he cares deeply about user experience, writing elegant code, and building reliable systems. During his career, he has focused on solving the challenges of large-scale distributed systems and contributing to open-source projects. He is active in the open-source community, is always curious and passionate about cutting-edge technologies in the software engineering world, and aims to create powerful features and build stronger systems. So without further ado, I will pass it to Hao.
Thanks, Effie. Let me share my screen. Can everybody see my screen? Cool. Hello, everyone. My name is Hao Geng. Today, I'm very glad to share some of our exciting work to you. Before we start, a bit about myself. I'm working at the Kafka services team at LinkedIn. Our team is responsible for building reliable and scalable Kafka services for the company. And I've been working here for a little bit more than 1 year. And I've been working on solving scaling challenges on Kafka. Besides, I also work on some other services in Kafka ecosystem. One of them is Cruise Control, which is an open source tool to manage Kafka clusters. Before joining LinkedIn, I worked at Apple for about 4 years. So that's enough about me, and let's get started. Today, I'm going to share how LinkedIn cleans up the unused metadata for its pub subsystem. Here's today's agenda. We will have 4 sections. First, we will give a brief introduction on metadata pressure. What is that, etc. Next, we'll go through our solution for reducing the metadata pressure, the topic GC service. Then in the third section, we will show some performance impact of topic GC. And last, we'll discuss some future plans for the service. All right, let's jump into this first section. In this section, we will discuss what is metadata pressure and how does it affect our pub subsystem at LinkedIn. To begin with, let's take a brief look at our pub subsystem. We use Kafka as our core part of infra at LinkedIn. Apache Kafka is a popular open source PubSub system. Here at LinkedIn, we have more than 100 Kafka clusters, and in those clusters, we have more than 8,000 brokers. In total, we have nearly 500,000 topics in those clusters, and the clusters are receiving more than 21 trillion messages per day. With that massive usage of Kafka, we certainly have encountered many challenges when scale Kafka clusters and some reliability issues for sure. But today, let's just focus on the challenge of Kafka metadata pressure. And we'll explain further what is that in the following slides. Before jumping into so many details about metadata pressure, let me briefly talk about how Kafka works. I'm pretty sure a lot of you may have already be very familiar with Kafka. Some of you may have used Kafka a lot. So this part is just for folks who are sort of newer to Kafka and not quite familiar with Kafka internals. So Kafka has this concept topic as a data transmission unit. Users can create topics together with some producers and consumers. Producers send messages to the topic and consumers read from the topic. For topic, it can have multiple partitions. And for each partition, Kafka maintains several replicas for fault tolerance purpose. The replicas reside on different brokers, and the communication between replicas conforms to the leader-follower model. Basically, the follower replicas periodically fetch data from the leader to keep in sync. So let's take the diagram on the right side as an example. Assuming we have a very small cluster, there are two brokers in the cluster, broker A and broker B. Again, for simplicity purpose, let's assume there are only two topics in the cluster. Topic 1, which is in color blue, and the topic 2, which is in color green. Let's assume each topic only have one partition, which has two replicas. One of the replica is the leader, and the other one is a follower. Notice that the follower and the leader of the same partition cannot reside on the same broker because otherwise it will be single point of failure, right? If a broker dies, the partition will be offline. It is also worth noticing that in Kafka, producers and consumers only talk to leaders. So in order to keep sync with the leader, for topic 1, partition 1, the blue topic, the follower needs to send fetch request to the leader. In other words, broker B needs to send fetch request to broker A. For the same reason, topic 2, partition 1, the green blocks also needs to keep in sync. So the broker A also needs to send fetch request to broker B. In other words, the two brokers actually need to send fetch requests to each other to make sure the replicas on them keep in sync. This is just a very high level view of how Kafka works. As what we explained, topics act as the user interface for Kafka. Users can create as many topics as they want, sometimes just following business needs, sometimes just for testing. And sometimes there are services automatically create a lot of topics. Who knows? Quite often, when the business needs changes or the design changes, users would create new topics and abandon the old topics. This is understandable and reasonable. However, Kafka does not delete those unused topics by itself. As a result, in some worst case, there can be more and more topics in your Kafka cluster, and this will eventually cause some disruptive impact to Kafka. So how do unused topics affect Kafka? It can be a confusion for many people. Since unused topics are empty, then how can an empty topic with no data affect Kafka? I will explain that from 3 perspectives. First, empty topics has no data, that's true, but it does have metadata. Kafka needs to store the partition and replica assignments information in many places, including the broker metadata cache, Zookeeper, and even add the metadata as payload in some requests. For example, there's a request in Kafka called metadata request, which can contain all metadata of the Kafka cluster. The unused topics can add a lot of redundant payload to the metadata request and slow it down. And the second perspective, as we mentioned in the previous slide, followers send fetch requests to the leaders periodically, regardless of whether there's data in the topic or not. The more unused topics there, the more redundant fetch requests are being sent and handled. To handle those redundant fetch requests, the brokers can consume more CPU resources or even more memory, because Kafka needs to create something called fetcher thread to send and handle the fetch requests for unused topics. Last but not least, on controller failover, the new controller would load the whole cluster metadata, and it takes time. The more metadata there, the longer it takes for the controller initialization. Controller initialization time is crucial to Kafka because a lot of requests of Kafka are handled by the controller. During controller shutdown, the whole Kafka cluster can be in a very bad state, and unused topics can add unnecessary controller failover time. Those are all side effects caused by unused topics or by the garbage metadata. The impact might not be obvious if you don't have a lot of unused topics in your Kafka cluster. But if you do have a lot of unused topics, it certainly will affect the cluster performance and even break things. To give you an idea on why do we need to address this issue at LinkedIn, let's take a look at this graph. It gives us a brief view of the portion of used and unused topics in some Kafka clusters at LinkedIn. In this graph, each bar represents a separate Kafka cluster. The blue parts are used topics, and the red ones are unused topics. As we can see, in many Kafka clusters, at LinkedIn at least, there's a large portion of unused topics, up to 40%. So that's a real problem that we need to solve. All right, now that we have discussed the issues brought by those redundant metadata, let's see how we can solve it. In this second section, we'll discuss our solution, Topic GC. Basically, it's a service that we built to automatically detect and delete unused topics. To design such a service, we will have a list of requirements, right? So first, apparently, it should be able to detect and remove unused topics from the cluster. Next, it should let the topic owners be aware before the topic deletion, because sometimes the topics are just temporarily unused, and the owner should be able to reject the topic deletion for such topics. What else? Another important requirement is it should ensure no data loss. For example, if there are messages written to the topic during the topic deletion process, the data will be lost, and we should definitely avoid it. Last but not least, take care of the dependencies. What does it mean? It's possible that other services can depend on some unused topics, and before deletion, we'll have to unbind those services from the topics. Given those requirements, here's how we design Topic GC. The Topic GC service is designed as a state machine, as shown in the diagram. Each block represents an individual state, and each arrow represents a different job. The jobs are running in background periodically, and each job turns the topic from the current state to the next state. The good thing about it is we can easily enable or disable any individual job without shutting down the whole service, and configure the execution schedule of each job separately. Now let's go through how Topic GC works. To begin with, there should be a usage detection job to detect topic usage and mark a topic either used or unused. For unused topics, Topic GC sends notifications to the topic owner, say, hey, we're going to delete your topics. Please take actions if you want to keep the topic. And then we'll give the user some grace period. If we still don't hear back from the topic owners, topic GC will mark the topic as user wait done state and start to block topic write access. Once the write access are blocked, it disables the mirroring for the topic. I will discuss what does mirroring exactly means later. And after all of those preparations are done, topic GC can finally go ahead to delete the topic and change the state to deleted. During the whole process, if usage is detected on the topic GC will mark the deletion as incomplete and roll back the states all the way to used. So this is an overview of how topic GC works, and I'll explain each step in more details. The first step for topic GC is to decide whether a topic is a garbage topic or not. To achieve it, we have a list of criteria to determine if a topic is used or not. First of all, there should be no data in the topic. The topic has to be empty. Then there should be no bytes in or bytes out for the topic. So bytes in, bytes out are metrics that are emitted by Kafka. Besides, there should be no produce and consume request sent to the topic. How do we know that though? So LinkedIn internally has some access service, mainly for security reasons. As the diagram shows, we have a wrapper on top of Kafka to make sure all the Kafka requests, including producing and consuming requests, must go through this access service. And the access service will record the producing and consuming events into some storage so that topic GC can query the produce and consume event from that storage. That's how topic GC knows whether there are read or write requests to the topic. Last, we have another criteria that we should not delete topics that are newly created. It totally makes sense that some new topics don't have traffic yet, so we shouldn't treat them as garbage topic. With this criteria, topic GC can determine whether it needs to delete that topic or not. The next step is to notify users for unused topic. It is important to let the topic owners know before doing any admin changes to the topic. There can be cases that the topic is not used for quite some time, but users still want to keep the topic for some reasons. In those cases, we want to keep the topic for the users. From another perspective, the good thing about this notification is users can reach back to us when we mark the topic as unused by mistake. For example, maybe due to some code bugs or some other issues, we send an email to the owner of an active topic and says, hey, we will delete your topic because it seems to be unused. The user will likely reply with, well, that's actually not true. We're using that topic right now. So please don't delete that topic and maybe figure out why it is marked as unused. Then we will immediately realize that, oh, maybe we're doing something wrong here. Let's figure out why topic GC make such mistake. This has actually helped us to identify several issues before. So in our solution, we choose to use emails as the way to notify the topic owners. To be extra safe and cautious, we send two notices, a 30-day notice and a 7-day notice. If we don't hear back after 2 emails are sent, we will trigger the next steps. The next step is to block write access. This step is also very important because we want to avoid last-minute write. For example, a client can produce messages to the topic during the deletion process, and the messages can be deleted with the topic before the consumer attempts to read from the topic. To prevent such data loss, remember we mentioned we have an access service internally. We will leverage that service to block write requests to the topic. As for read access, we still allow users to read or consume from the topic during the topic deletion process. If we detect any consume request to the topic anytime before the actual deletion happens, we'll terminate the whole deletion process and for that topic and roll back the state all the way to used. After topic accesses are blocked, we need to disable mirroring. At LinkedIn, many Kafka clusters are mirrored by Brooklin. Brooklin is an open source tool to stream data from source to destination. I think we will have another session today to talk about Brooklin in more details. But here we can just regard Brooklin as a consumer to consume from the source cluster, plus a producer to produce to the destination clusters. It's called mirroring because the destination cluster will have the same data with the source cluster. Since Brooklin subscribes to all topics, and if a topic being mirrored is deleted, Brooklin will throw exceptions. We need to avoid that for sure. So we have to remove topic from its subscription list before the topic deletion actually happens. So here, Brooklin is just one example of a service that can be dependent on the topic existence. To sort of expand the concept, we should make sure that all other services that are dependent on the topic to remove the topic from their dependency list before topic deletion. And here we go. We finally reached the last step, topic deletion. It is actually quite straightforward compared to the previous steps. Topic GC delete the topics through Kafka, the main client. And you probably don't want to delete 1,000 or 10,000 topics in one single batch, because that will generate a long request queue and may result in outage. So we delete the topics in smaller batches. To be extra safe, we execute the deletion one fabric per day, just in case there's anything done wrong. We don't affect, every places in LinkedIn. With all of those being said, let's see how did topic GC perform. So we launched topic GC in one of our largest data pipelines. It contains 3 clusters and over 600 nodes. In this graph, each color represents a separate Kafka cluster. Before deletion, they have in total nearly 12,000 topics, and we reduced the topic number by around 20% with topic GC. Next, let's see how it affects metadata factor. Metadata factor is how we measure the metadata pressure. It is calculated by replica count times by broker count, and can roughly reflect how much metadata are stored in the cluster. This is because in Kafka, each broker stores a complete copy of the metadata for the whole cluster. The metadata factor are dropped from 410 million to 330 million. With this data, I think it is fair to say that we reduced the metadata pressure by 20 to 25%. The CPU usage also dropped by around 30%. This can be explained by there are less fetch requests in the clusters. Because topics are deleted, the total number of leaders and followers are also reduced. So essentially, we get rid of a lot of redundant fetch requests from followers to leaders. So that's why the CPU is less used. Just to clarify that the y-axis here is the accumulated value for CPU usage. Say we have 600 brokers, right? When the total usage is 150, that means the average CPU usage on each broker is 150 divided by 600, which is 25%. This is just for you to how to read the graph better. The performance of many types of Kafka requests are also improved. Here, we listed the produce requests and metadata request as examples. And the request performance are improved by up to 40%, which is a pretty good result. In this last section, we will discuss our future plans for Topic GC. So the first plan, we are going to onboard Topic GC to all Kafka clusters in LinkedIn, hopefully. So currently we have made it on several different pipelines and have been seeing pretty good results. And we'd like to leverage the service for all other clusters if possible. So that's the first thing. The next effort we're going to do is to try to evaluate the business impact of Topic GC. Since a lot of topics are deleted, we sort of anticipate that we probably don't need the same amount of brokers for the clusters after topic deletion, right? So if we can reduce the number of brokers, that will be the cost saving for the whole company, and everyone will be happy to see that. The last one is about another potential area for huge improvement. Basically, Topic GC today only covers the topics that has no read and no write requests. Other than those topics, there are some topics that we call black hole topics that only have producers but no consumers. Those topics can have a lot of data, consuming lots of resource, disk usage especially, and no one is using them. If we can identify and delete those topics, the impact will be even much larger than the current Topic GC. The challenge here, though, will be like how to make sure those topics are really, really unused, as the highest priority for Topic GC is still to avoid data loss. We definitely don't want to delete any data that are still needed by someone, right? So those are all the efforts we wanted to make in the future. And hopefully Topic GC can take on more responsibilities and help us better. All right, those are all of the stuff I wanted to share today. And we have published an blog of Topic GC on LinkedIn engineering, and you can find more details there. I've attached a link here in this slide, or if you're interested, you can directly search for Topic GC on either LinkedIn website or Google. And I'm pretty sure you can easily find this blog. With that being said, I hope you all enjoyed this presentation, and thank you so much for listening.
Thank you for the great talk, Hao. So it was very informative. There are some questions under Q&A, so we have some time to maybe take some of them live. So if you can maybe sort it based on most upvotes, so that we go with the popular questions first. And for the ones that we can't answer now, maybe you can answer them offline during the meetup.
Okay, let's see. So sorted by most upvotes, right?
Yes.
Is it possible to delete some old Kafka?
And also, can we read the name of the person asking the question? Yeah.
Sorry for that. Yeah, so this question is from Vadim Mikhailov. So the question is it possible to delete some old Kafka topics manually? Last time I checked, manual deletion was almost impossible. So the first thing, there is definitely some way to delete Kafka topics manually. You can do that through the admin client. So at LinkedIn, though, we don't allow users to delete their own topic for some reasons. And I think the most important reason is that, as we mentioned before, topics sometimes are dependent by some other services, like Brooklin and some other internal services. So it's totally possible that the users are not aware of such thing. So when they delete the topics, they may break the other services that depend on the topic. That's why we don't allow the users to do it themselves internally. But I guess if you don't have such policy, or if you don't have such worrying concerning, it's still possible to do it. Yeah, that's the answer. Yeah, so next one is from Malay Baseball. And the question is 21 trillion messages per day. I will give a yes to that answer because we have, this number is not a single Kafka cluster, is for all clusters accumulated value at LinkedIn. So at least for me, it's a very big number, but that's today's true metric. So that's the answer for that. The next one is from Gary Stillman. The question is, I actually see some answers under that. Do I still need to answer this question here, or I think Greg.
Yeah, I see that Greg answered it, but there's a follow-up question there. Maybe you can take that offline for the discussion and go to the next one.
Okay, sounds good. Yeah, I'll make sure follow-up questions are addressed. The next question is from Mike. I also see Greg answered that, but let me just read the question aloud. So speaking of Zookeeper, is LinkedIn migrating to Kafka 2.8.0 plus? So that's something. Yeah. So that Zookeeper is no longer required, and it is replaced with Raft. So the question is asking about, do we migrate to the new world without Zookeeper, which is correct, where we have some plans to do that. Some reasons are, it can avoid us using Zookeeper to avoid some Zookeeper side limitations. Like it has a limitation of the total topic name length has to be no longer than something. Otherwise, there will be some failures. And we have some other reasons of migrating to Craft. So yeah, the answer is yes, we have planned for that. That's the answer. And I see some questions are popped up, actually. Now the question that's ranking first is from Gary Stillman. Would black hole topics possibly include audit logs that are not accessed frequently, except in case of security incidents? I think that's actually a very good point. And that's exactly part of the reasons that we haven't taken any actions for black hole topics. And the exact challenge here is it's really hard to determine whether this topic is still used or not, because there are still data in that. So we want to really make sure that it's super safe to delete the topic. No one is using that at all before the topic deletion. So that's something we definitely need to take care before to delete those black hole topics. And there are some other questions, but I think we're almost out of time for my session. Is that possible if I can answer that offline?
Sure. Yeah, I think we're almost at time for the next talk. Once again, thanks, Hao, for all the answers. And I will leave it to DJ for introducing our next speaker.
Thanks again.
Thanks, Hao. Thanks, Efe. I'd like to introduce our next speaker. Kasun is a senior product manager at Microsoft working on Azure messaging services. He's a product manager and software architect with extensive experience in microservices, event streaming, and cloud-native architecture. He's author of 3 different O'Reilly books: Design Patterns for Cloud-Native Applications, gRPC Up and Running, and Microservices for the Enterprise. And he's been been a speaker at a number of conferences such as KubeCon North America, O'Reilly Software Architecture Conference, and GoToCon. And he's going to talk to us about event streaming with Kafka using Azure Event Hubs. Please take it away, Kasun.
All right, thanks, DJ. Let me share my screen. Oh, if you can stop sharing.
How? Can you hear us? You need to stop sharing it for the next speaker.
I think I click pause share. Oh, sorry. Yeah.
Oh,
thanks.
Oh, thanks, Hal.
Sorry about that.
Okay, let me share it again. All right, hope you can see my screen.
Yeah.
Okay. All right, thanks everyone. So in this session, I'm going to cover event streaming with Kafka using Azure Event Hubs. So I'll give you a quick introduction to Azure Event Hubs and its Kafka capabilities. And also I'll walk you through a quick demo of using Event Hubs to implement a Kafka application using Kafka compaction. So without any further ado, let's get started. I think we discussed about myself with DJ's intro. So let's start the session with a quick overview of the business use case for event streaming. And we all are in event streaming meetup, event stream processing meetup. So I don't really have to emphasize the importance of event streaming, but we keep on seeing quite a few business use cases emerging around high volume event processing, primarily built around event streaming engines such as Kafka, Azure Event Hubs, AWS Kinesis, and so on. So there are so many applications that are producing very large volumes of events, and as a business, we really need to process all these different events and generate business insights out of those events. So there can be use cases around web click streams in the financial sector. There can be use cases related to anomaly and fraud detection, processing application logs, processing IoT sensor data, real-time ETL, and processing change data capture. So in all of these use cases, it is quite important to sort of building an end-to-end event stream processing pipeline, starting from event capturing, event storing, and finally processing them and generating insights. So that is where the event streaming platform concepts come into the picture. So in the context of event stream processing platforms, we can identify, now if you look at the concept of an event, right? So it's the event is the fact that something has happened at a specific point in time. And then if you have such events in sequence in a related way, then we call it an event stream. So as part of most of the business application development related to building these big data processing pipelines, so you often deal with event stream processing and event stream ingestion. So if you look at the different phases in an event streaming platform, you can identify you have the event triggering phase, where you sort of create different events as well as capture events coming from different sensors and different sources. And then once you capture them, you basically have to store them, ingest and store them, right? So that is where all these event brokers come into the picture. So, and once you store them, then you can build event stream processing logic on top of it. So you basically process the events stored in this event ingestion engine using technologies such as Spark, Flink, and if you are running on Azure, you can use services such as Azure Stream Analytics, Azure Databricks, and so on. So once you process this data, then you generate all the business analytics, business insights, and then you present them through model and serve layer. So as part of today's talk, I'll be talking about primarily about event ingestion, where event hubs come into the picture, and talk about the Kafka capabilities of event hubs. So I'm sure some of you have heard of Azure Event Hubs. So it's a fully managed real-time data streaming platform as a service. So it can stream millions of events coming from different sources to different destinations with low end-to-end latency. It is built around the concept of partitioned consumer model similar to Kafka, where you have event hubs or topics where you can organize events into topics, and then inside a topic you can have multiple partitions to parallelize the event streaming. So it is built on top of a multi-protocol event streaming architecture. So by natively it supports AMQP through the SDKs that we provide. At the same time, we have native support for Kafka using the Kafka protocol head. So that is where all the that is where you can run Kafka workloads with Event Hubs without changing any code. And as part of the Event Hubs component architecture, we have different consumer groups that are connecting to Event Hubs. Similar to Kafka, you consume these messages independently based on their consumer requirements. And as part of this, you can also integrate Event Hubs with Event Hubs natively with Azure services such as Azure Stream Analytics, as well as any other open source technologies, things such as Spark. Since we have the Kafka compatibility, any Kafka consumer technology can be used against Event Hub simply by changing the endpoint to Event Hub. So we provide industry-leading performance, reliability, availability, and cost efficiency. So I'll talk about some of these technical details in the upcoming slides. Now, Event Hubs is not necessarily a Kafka broker, right? So Event Hubs, if you look at the internal architecture of Event Hubs, we don't really run or host Kafka clusters or Kafka runtimes inside the Event Hubs. So what we have done is rather offering a managed Kafka solution. We built Kafka as a protocol head to our existing event streaming engine of Event Hubs. So because of that, we were able to support multiple protocols like AMQP, Kafka, and HTTPS for event ingestion. And on the consumer side, we have AMQP and Kafka. So as part of the Kafka compatibility, we offer support from version 1.0 to the latest version. The current compatible version is version 3.x. And when you are migrating applications, your existing Kafka client applications to Event Hub, you just need to change the Kafka, the broker endpoint and the security context. That's all you have to do. So therefore, any Kafka library that you are using with maybe with your on-prem Kafka clusters can be seamlessly brought into Azure Event Hub. So when you get a single stable endpoint, you don't really have to deal with a set of broker endpoints. You have a single broker, a single stable endpoint to all your Kafka applications. And Event Hubs will take care of routing the request to the specific topic partition that you want to route the request to. Since it's been developed as a separate protocol head, there are some feature gaps that we are currently having, like we don't have the full support for Kafka transactions, compression, and streams, which we are working on narrowing down in the future. So terminology-wise, Event Hubs, we organize topics or Event Hubs entities into an Event Hubs namespace. You can think of it as a Kafka cluster. So inside a namespace, you can find one or more topics. So inside a topic, it is the same terminology as with Kafka. You have multiple partitions, and then you have different consumer groups at the consumer side. So there are a few reasons that why you should use Event Hubs for Kafka. I'll only cover the technical aspect of this. So basically, one of the main objectives that we have as part of this service is to simplify your Kafka event ingestion experience. So basically, you don't really have to run or manage Kafka clusters. You don't have to deal with the complexities that comes with Zookeeper, K-Route, and so on. So you have a fully managed Kafka offering and with a single stable Kafka endpoint. And also it can scale from few megabytes per second to several gigabytes per second scale. So performance and reliability is one of the main areas that we are outperforming most of the existing Kafka providers. So we offer end-to-end latency of 10 milliseconds with our higher end tiers, such as premium and dedicated tiers with minimum latency jitter from external tenants. And also moving on to cost efficiency, it's something like if you're planning to use Event Hubs, it's something we highly recommend to compare with other solutions as well. So we managed to basically offer a cost-efficient solution based on our internal architecture and ability to get more out of less resources. And being part of Azure, you get all the other Azure security, compliance, and availability features, and things such as zone redundancy, GODR for without any additional cost. And let's talk a bit about the multi-protocol event streaming experience in Event Hubs. So as I said, we implement different protocol heads to support different event streaming workloads, right? So we initially started with AMQP as the main native protocol of Event Hubs, and then we included Kafka as another native protocol. So because of this addition, it made the Event Hubs more interoperable with other clients, most of the Kafka clients out there, as well as with this architecture, you can mix and match these different protocols. So for example, you can have a Kafka application ingesting data to Event Hubs. At the same time, you can process and do real-time streaming analytics using a separate Azure service, such as Azure Streamline Analytics, which is connecting to Event Hubs using AMQP. So in that case, you have incoming Kafka and outbound AMQP. So likewise, you can mix and match these protocols. And given that Kafka is an RPC protocol, there are certain use cases that AMQP might be conducive to conducive more. So in such cases, like you might be able to get better performance out of AMQP workloads than Kafka, especially when it comes to idle connection handling and with heartbeats, as well as the overall resource utilization may be low when you try with AMQP. So the idea is not to force our users to use this protocol and that protocol, but if you have a requirement to use Kafka, feel free to use it. You'll get the same performance when it comes to latency with Kafka, but you always have the option of choosing and mixing match these different protocols. Then this is about the different tiers that we offer. I don't really need to talk about the business aspect of these tiers, but the architectural differences between the tiers are more important in this session. So we have standard, premium, and dedicated SKUs. Standard tier is, we recommend them for sort of small scale workloads, and it's a multi-tenant offering that can scale from few megabytes to up to 40 megabyte per second scale. Since it's multi-tenant offering, you may see relatively high latency compared to other SKUs, as well as you may get cross-tenant interference based on how other tenants behave in the environment. And if you need better isolation, better latency, and better performance, then our recommendation is to use premium SKU, which is built on top of a separate architecture from standard tier. So we, with premium, we are using reserved capacity model. We have reserved memory and compute capacity, along with two-tier storage engine architecture. So each VM that powers the premium SKU has a local storage, which drastically improve the end-to-end performance. Then moving on to our dedicated SKU, this SKU is primarily a single tenant fully owned by you. So you can use it to achieve gigabyte per second scale of throughput, along with less than 10 milliseconds and even P99.99 with which is less than 100 millisecond for majority of the workloads. So I would say the dedicated SKU is the sort of our recommendation to use in a mission critical workload that you really need low latency as well as very high performance. So all the changes that I explained earlier, like the introduction of two-tier architecture, so those changes have been done in very recent years. We launched our premium SKU with all these different architectural changes back in late 2021, and with all these changes, we have been consistently testing Event Hubs for event streaming performance, and we continue to see we continue to achieve less than 10 milliseconds of end-to-end latency for majority of the Kafka and AMQP workloads with our premium SKU. And we have been using Open Messaging Benchmark to benchmark our product, which is an open source tool. And also recently we introduced our next version of our dedicated cluster, where we did the same multi-tier storage engine architecture with upgraded underlying infrastructure. So with these clusters, as you can see in the graph, we were able to achieve less than 10 milliseconds of average latency, as well as pretty much less than 90 milliseconds of P99.9. So these numbers may be in some cases better than your own running your own Kafka cluster, and obviously better than most of the Kafka managed offerings out there. So and maybe coming with the fraction of the cost of similar services, as well as you don't really have to manage these dedicated clusters, because it's fully managed for you. And finally, let's talk a bit about the high availability capabilities. So Event Hubs comes with, by default, comes with a replication model within a one cluster. Events are replicated across the cluster, across 3 different fault domains. So every topic partition is replicated 3 times by default. And out of these replicas, there will be one primary assigned, similar to Kafka, but internally we run these workers on top of a coordination framework, which built on top of Azure Service Fabric. And then this is within one cluster. And if you want to make it zone redundant, you can simply choose a zone that choose a region that has zone redundancy. So with zone redundancy, you will get 3 physically separated data centers running the same Event Hubs cluster or Kafka cluster, and they are seamlessly replicating data. So existence of zones are not really visible, so you seamlessly switch over between these zones without changing any code or configurations. And the good thing is zone redundancy and zone capability comes by default with product with no additional cost. So yeah, so I hope that gives you some understanding about the capabilities of Azure Event Hubs. Now I would like to walk you through a quick demo of using Event Hubs in a typical Kafka integration example. For this one, I'll be using Kafka compaction feature. In this case, I'm using 2 Kafka applications, producer and consumer, who's sending data to Event Hubs. Then we created a Kafka compact topic in Event Hubs and see the behavior. So let me bring up my all right. So before we jump into the details of the demo, let me quickly explain the concept of log compaction in Event Hubs and even in Kafka as well. So log compaction at very high level, it's a mechanism to retain data. So usually in Kafka, you retain data based on time. So we do time-based retention. But in certain cases, you may have to retain data based on the key, right? So with the compaction retention policy, you will only retain the latest events of a given event log. So suppose in the case of this example, you have an event log. You are using this event key or the partition key to keep track of all the events that you received at your log, event log. And you will, after the compaction job, you will only retain the latest value for it. For example, if you look at the key value K1, you will only maintain the latest version 6 of this value. So once the compaction is done, you can shrink the event log and reduce the size. So the way it works in Event Hubs is, as I mentioned earlier, in Event Hubs, you create the Event Hubs topic inside an Event Hubs namespace. And when you are creating the topic, you have the option of selecting the retention policy. Now, with that, let me quickly show you the Event Hubs portal. So as part of the Event Hubs service, you can create an Event Hubs namespace, and inside the Event Hubs namespace, you can create an Event Hub. So you can think of it as a Kafka topic, right? So when you're creating an Event Hub, so you have to provide the number of partitions that you will need, name for the topic, as well as the cleanup policy. So by default, it will use the delete cleanup policy, but here I'm using the compact cleanup policy. Now here I have a similar topic that I have already created, Contoso compacted topic, which has the cleanup policy as compact. So now suppose you have a Kafka application that you want to integrate with Event Hubs. So to mimic that, I have two Kafka applications. Now this one is written using Java. It's a generic Kafka application. If you look at all the libraries that we have, we are pretty much using all the generic Kafka libraries. Same with this is the producer and this is the consumer application. Same with the consume. And so to integrate this application with Event Hubs, what you have to do is you simply need to change the producer configuration. So as part of the Bootstrap servers, you have to use the Event Hubs, the host name or the namespace endpoint, and then only you need to change this SASL Jazz config. So that's all you have to do. You don't have to do any other code changes in your actual Kafka application. So it's a mere configuration change that you have to do at both producer and consumer side. So let's take a look at how you can retrieve the endpoint address here. If you go back to the namespace, you can retrieve the host names from Event Hubs namespace host name. And then you can go to the shared access policies to retrieve the required security context information. So once you retrieve them, you just basically need to update your configuration that I showed you earlier here. And with that, let me also show you. Now I'm running my client application in a VM. Let me pull my consumer as well. So I have two applications. One, this is my producer. So I'm running my producer application from my VM, and I'm ingesting data to Event Hubs from my producer application. So as part of the producer, what I'm doing is I'm sending different set of events. If I show you the example, producer code. So I'm sending two set of events. Since I'm trying to demo the compaction experience, I'm sending a batch of events from 1 to 100 with the key value. And then I'm using V1 for the value of the event. And then I'm updating same set of keys again from 1 to 50. So ideally, if the compaction job is completed, you would see the latest events from 1 to 50, while you will see old events version 2 from 1 to 50. Now I ran the consumer application. I can also check my console and see whether I have received messages. So it starts to getting new messages into my Event Hubs namespace. Let me refresh it. Yep, it will show up in a minute. So in the same time, I'm running my consumer, right? I can also go inside my compact topic. Yeah, starts getting some messages, and then on the consumer side, I can also start my consumer. So as you can see, compaction job has executed, and you would see events coming from some of the events are already being compacted. So you didn't see any events from 1 to 31, and some are being replaced with version 2. Like these are with version 2. So compaction job runs as part of the Event Hub. So in order to invoke the compaction, since compaction job is based on the size, I intentionally create an event with 1 megabyte message size so that I can quickly trigger compaction. So integrating with Kafka application is that easy with Event Hubs, right? So you don't have to do any other changes. As part of here, what I'm doing is I'm running an Event Hubs namespace in a dedicated cluster. So as part of the namespace, you also get other features such as any Azure capability, including all the security features, Azure Active Directory integration, and we have features like built-in audit log support in Event Hubs so that you can monitor all the data plane operations. Yeah, so that's basically what I plan to demo, and we can also look at the metrics related to, yeah, you can see incoming request as well as the number of messages in Event Hubs portal as well. Right. Yep. Yeah, that's basically what I plan to cover today.
Excellent. Yeah, thank you. Kasun, I don't know if you want me to read some of the questions from the Q&A in the chat, or if you want to maybe sort them by most upvoted, and if you want to answer a few.
Sure. Yeah, let me try that.
I think there's at least one lingering. How answered almost everything, but I think there's might be one lingering question from his presentation, but everything else I think is new for you.
Mm-hmm. Yeah, there's a question on schema registry or anything similar for message versioning. Yes, we do have the built-in support for schema registry. I can actually show it to you in our Event Hubs namespace. As part of the Event Hubs namespace, you get a schema registry instance integrated to it. So this is where you can create your schema groups. We currently support Avro as the serialization support. We will be having JSON schema support in near future. So you can use it for all the schema-driven messaging for all your Kafka workloads. How does the Kafka? There's another question on how does the Kafka compaction works with offset from Flink. So with offset, basically, I think the question is, since we are getting rid of all the messages within a given event log, right? So we are basically getting some of these offsets. So the translation will happen automatically within the Kafka broker level, so you don't have to explicitly do any changes to the offset. So as part of the Kafka or Event Hubs, your Kafka applications are basically you don't have to change anything related to offset. How much? There's another question from Noan. How much time it took for you to get the perfect understanding of both Kafka and Azure? I think I'm not sure whether that's related to like any technical details here, but yeah. So if you basically if you plan to use Event Hubs and if you're familiar with Kafka, let's say, I think you can easily map all the Kafka concept into Event Hub. There can be few like Azure specific things that you have to, like very few things like using AD maybe and using Azure Event Hubs portal. And apart from that, if you are a Kafka developer, and migration would be very, very smooth. So you can directly apply, as I showed you, right? You can migrate your Kafka application without doing any changes, as well as you can apply the Kafka concept directly with the Event Hubs. There's another question, is Event Hubs open source to deploy on other cloud providers? No, currently we only offer Event Hubs on top of Azure only. But our we always embrace all the open standard. We are part of AMQP open group, and we are contributing to CNCF schema registry APIs as well. We are part of all the open messaging and open specification groups, but Event Hubs as a product, as a service, is not open source. So there's a question on what is the best practice to another question. Does Event Hubs support WebSocket from Prasad? Yes, we do support WebSocket on top of MQP. Another question from Deepak on schema registry out of the book support for Event Hubs. Yes, we have, as I showed you, we have the out of this book support for schema registry, and it comes built into your namespace. So once you create a namespace, you can start using the schema registry. So if you use Kafka streams, this underlying execution stays the same as other Kafka. So yeah. So we have the support for Kafka streaming API, but if you want to use proprietary implementation such as KSQL DB on top of Event Hub, that won't work. So in most of the Kafka and Kafka streaming use cases, you should be able to implement with Azure Stream Analytics. We have the built-in capability in Azure Stream Analytics with a built-in no-code editor, where you can use basically inside one of these event hubs. So you can go to one of these events and start processing data using process data capability, right? So we have a built-in low-code editor or no-code editor where you can graphically process them, and under the covers we use Azure Stream Analytics. Is it possible to perform compaction on badges? So currently compaction job, controlling the compaction job is primarily handled by the service based on the size of the dirty and clean section of the log. So when the dirty section goes beyond, dirty segments go beyond certain size, then only the internal compaction job kicks in. So currently you can't control it. I think that is the same case with other Kafka cloud services as well.
Thank you.
Okay. All right. Thanks for all the questions. And,
Thanks again.
Thanks for the feedback.
Okay. All right, so let me introduce my colleague from LinkedIn, Shantush Venkatamran, for the last talk in this evening. Santosh is a staff software engineer on the Flink and Samza team and has been in LinkedIn for the last 6 years. His interests are broadly in different aspects of distributed systems, ranging from resource efficiency, fault tolerance, reliability, performance, extensibility, and operability. So being with Stream Platform team, he has worked on Samza as library, auto-scaling, enabling stateful Samza jobs, and most recently on the managed Flink SQL service. All right, Santosh is going to talk about Brooklin, change data capture using Flink SQL. All right, Santosh, pass it on to you.
Thank you, Gary. Can you guys confirm if you can see my screen?
Yes.
Okay, thank you. Hey guys, thanks for taking time to attend this meeting. My name is Santosh. I work on the streaming platform team. So in this talk, we're going to cover, or we're going to just see what is change data capture, and we're going to see change data capture with Flink SQL and Brooklin, and how we use that for like mission critical use cases in production at LinkedIn. So the agenda for today's talk is like we want to give an overview of Brooklin, and Brooklin is a CDC system at LinkedIn, and we will talk about. I want to give an overview of the connector that we built in Flink, which was consuming the change capture data from Brooklin. And third section, we want to talk about the common change data capture pipeline patterns, and then like some use cases that we have in production right now, like. So this is the overall agenda for today's talk. So before we go on, I just want to give an overview of like what is change data capture, right? So if you take a look at LinkedIn as a company, we were primarily Oracle like house. Most of the services used Oracle as a database, and over time we evolved into using like document store like Espresso, and then like using data stores like MySQL. Etc. So essentially, like what the common use cases that we have seen at LinkedIn is that like we want to have like a real-time processing of changes happening on the source database. Let's say if you have source of truth database being Oracle, for example, and there are some bunch of updates happening on the database, we want to actually like watch for those updates and like have external system process that update, and maybe like build services that can actually like affect the LinkedIn user experience. So one of the examples could be like, say, for example, you are updating your, let's say you have a LinkedIn member, you are a LinkedIn member and you have a LinkedIn profile, and you are like, for example, you are like changing your job from company A to company B, right? So one of the common thing is to basically update the search indexes that LinkedIn serves, rather than if you research company A before your update, your profile has to show up, but after your update, the new company has to show up. Like if they search for the new company, after you make your update, like the company B, like your profile has to show up, but before the update, before you make your update, if they search for company A, your profile has to show up. So these kind of like real-time use cases that we wanted to support. Let's say another example could be like we wanted to figure out in real time to figure out which users to block. Let's say like we have some users creating spam and like defrauding users. We basically have a spam detection team, which basically figures out security team at LinkedIn, which figures out, okay, this particular member is actually like creating spam, and they want to block that particular member before they actually cause damage to the rest of the LinkedIn ecosystem in real time. So these kind of like use cases that we wanted to support, where we have a source of truth, which is basically being present in a database like Oracle, MySQL, or we have a document data store, Espresso, and we wanted to consume the changes that happens on the main source entity and some auxiliary entity that the service maintains. And we have these nearline data processing pipelines that will actually like do analytics or some kind of like preventive actions or like update indexes, etc. So this is called as change data capture, where we consume the changes from the source in the form of a bin log. If you have come from MySQL landscape, this concept of a bin log, which basically contains a sequence of all the changes that happens on a source DB, we consume this and then we process it. So there are two ways of going about the change data capture. One is a query CDC, and second is a log-based CDC. So the problem is to get the changes that happen on a source of truth database in real time. So in query CDC model, you will basically like periodically like run queries. Let's say like For example, every 5 minutes, you basically run some kind of a query, like figure out what are the tables or rows that were changed since last 5 minutes, and then you will figure out the delta set, and then you want to process that batch. Obviously, one of the problems is that you'll be hitting the source of truth database repeatedly with your queries, and when there are online services like trying to operate on the data, and once the number of applications which are processing these data changes, as well as the size of the actual data set size itself grows, it will become really not scalable. So you'll be like increasing the load on the actual database, and you'll be affecting the online queries. When I say online queries, the queries that you save to the actual user. And then like another problem with this kind of a query model is that like your deletes is not capturable. Let's say if a particular row is deleted, you'll not be able to figure out by the query you are running. Let's say figure out what are the rows that are changed in the last 5 minutes. And basically also enforces one of the problem is that like every schema, the database schema has to have something called as a last updated timestamp column, based on which you'll figure out like, and which is some kind of a enforcing that you're doing. And some data changes can get lost. For example, deletes or updates, they can get lost here. So these are the problems with query CDC. So as far as I know, we don't use that in LinkedIn. We use a model called log-based CDC, where we capture the data changes from the bin log, the changes that happen on the source of truth database. And this actually kind of has a low overhead on the source DB. By that, we mean that we are not actually coming onto the critical path of the read-write critical path of the online service. We'll be getting the bin log, the changes that happens on the database, and then we'll be operating on that. And these changes are actually like taken from the source DB, and they're actually published to a stream, which is later processed by the streaming applications. So in LinkedIn, we basically, the takeaway from this slide is like there are two CDCs, and we use the log-based CDC at LinkedIn. And why Flink SQL? Like so basically like Flink SQL basically gives us a flexibility to author streaming pipelines using SQL API, SQL as an API. Like we can author like real-time streaming pipelines using SQL as a dialect. So one of the major selling points is that like it kind of provides you a single unified API for both batch and stream processing. So this is a big benefit. Let's say if you're maintaining an offline pipeline and a nearline pipeline, if you're authoring your offline pipeline in Spark, and let's say your nearline pipeline in Flink, now it's as a responsibility of your team to basically ensure that these two pipelines, the logic in these two pipelines are same, are consistent with each other. So evolve these pipelines, maintain these pipelines, deploy and operate these pipelines is kind of like hard in production. So that's one of the main selling point of Flink SQL. That is, it kind of gives you a unified API. And also it supports like different kind of event time and processing time semantics. Let's say if you are coming from, if you're doing a stateful operations, let's say you can either do the wall clock time, processing time is the current wall clock time of your processor. You can do a stateful operation like a window or a join using processing time, or event time, the time at which the particular event was generated at the source. To basically do your like stateful join or window. Let's say you have infinite stream coming in and you want to like apply a window on that stream, tumbling window or sliding window. You can do that on any of these time semantics. And it also supports different kind of like UDFs. You have like a scalar functions which are applicable to a stateless transforms. You have aggregation and table valued functions. It has like a lot of flexibility around this, as I spoke about previously. It supports like different kind of streaming joins and aggregations. And the key selling point, I think, at least from our experience by offering managed SQL Flink SQL platform, is that like the ease of use aspect. Let's say if you're trying to develop let's say if you're new to a streaming landscape and you're coming to author a pipeline, the amount of concepts or amount of terminologies that you have to learn in order to author a pipeline in SQL is kind of very less. So it kind of like from the ease of use standpoint, it kind of gives the users who are trying to adopt Flink SQL a better experience or a seamless experience to author a pipeline. So these are the major reasons why we use Flink SQL at LinkedIn. Moving on. So I just want to talk about, since this talk actually covers about Brooklin, some of you might know about Brooklin, but I just want to like briefly touch about this and try to give you an overview of like what Brooklin is at LinkedIn. So Brooklin is a change data capture system or a streaming ingestion system which can actually like supports different kind of sources like Oracle, as I told before, like Oracle, sources or Espresso or MySQL data sources. It supports like the log-based CDC format, as we've seen before. That is like you take the changes that happen on like a Oracle, let's say table that is a source of truth maintained in Oracle, or let's say Espresso or MySQL, and you can stream that into a Kafka topic that the nearline or the real-time processing applications will consume. And it kind of like gives you a unified data format. Actually, by that, what I mean is, let's say like from our experience offering this platform at LinkedIn, we have seen that like a lot of use cases, a lot of pipelines want to consume data from different data sources. Let's say some cases they want to do a join between a table, or they want to basically like consume a data stream, a Brooklin data stream from based on Oracle table and a Brooklin data stream from Espresso table in the same Flink SQL application. So I think so for that, like this unified data format actually helps. Let's say if you have different data sources, like data sources could be Espresso, Oracle, etc., but the output format that Brooklin gives is kind of consistent. And as we spoke about, like isolation, like these applications do not actually like compete with the online queries. Online queries here basically means you have a REST service or RPC service, which is serving this data, the data that you have in your source of truth, which is doing a CRUD operations on the data. So this streaming application that you're writing or the real-time application you're writing is not going to compete with the online applications. They can evolve independently of each other. So basically, like as we spoke before, like they can scale independently of each other, and then it kind of enforces like policies here and governance. So by policy and governance, we mean like ACL, like access control list, which applications have access to the data, which data streams, and the monitoring in terms of strict SLA measures. Let's say Brooklyn basically offers SLA of not having any kind of data loss. Let's say you have data coming from a source, like a MySQL data source, and let's say it's populated into a topic. Brooklyn kind of like gives you a guarantee that there will be no data loss of messages. Messages will not be lost. And then like in some cases, like let's say you're trying to consume like a member profile data, the data stream itself could be encrypted. Like what I mean by that is that the individual messages that you have on the Kafka topic itself could be encrypted. So it basically supports all of these policy and governance on top of these change data capture system. And each of these, let's say if you have multiple applications, multiple like Flink SQL applications that are consuming from the same Brooklyn stream, each of them can be at a different point in time. Like let's say like one application could be at the beginning of the stream, another application could be at the end of the stream. So they can scale independently of each other. So this is the overall like a 30,000 feet overview of what Brooklyn is. And this diagram just like covers like what I just spoke about here, right? So we have this kind of databases here: Espresso, MySQL, and Oracle. These are the actual databases that are prevalently used for our online. When I say online, like REST services or like RPC services at LinkedIn. And we have like messaging system. Primarily messaging system we have at the message bus is actually Kafka. And we basically like this Brooklyn like streaming service or the streaming ingestion service will basically read the data from these sources and will populate that into Kafka, and then which the underlying consumers on the right hand side can consume from. So essentially, like you take data from like some table or Oracle or MySQL table, and then you kind of like when I say take the data, take the bin log data from this Oracle or MySQL table, and kind of like put that in a Kafka topic, which the streaming processes or the like a Flink SQL application or Samza application can consume. This basically talks in terms of like so basically like this again goes into like the deployment model of a Brooklyn service. Let's say there is one. Let's say every Brooklyn. Brooklyn basically uses Zookeeper for actually coordination. So we have like multiple instances of Brooklyn. So each instance can actually like have like this kind of a multiple mirroring pipeline. So we can just see here like when you say character 1 and character 2, they basically actually corresponds to a different kind of like a system. One connector can actually correspond to MySQL, and another connector can actually correspond to Oracle. And we also have this kind of producers like after consuming from MySQL, it can produce to maybe Kafka or maybe, for example, Event Hub, etc. So one instance will be chosen as a leader. So this leader will be responsible for ensuring that all the available work is distributed across the available Brooklyn instances. You have like 3 instances here. So this leader will ensure that this kind of a message or the data shipping from one source to the destination. That work is kind of distributed uniformly across all the instances. And then it uses Zookeeper for actually like both checkpointing and coordination, distributed coordination. This data stream management API is for actually creating pipelines on the fly. Let's say if you want to create a new Brooklin stream, let's say based on, let's say, a member profile database in Oracle, you'll be using this data stream management REST API to basically like create these data streams. And once a data stream has been created, after it's been created, Brooklin will basically get the data from a snapshot data from the actual table, and it will stream the data into the Kafka topic. And that the Flink SQL application or a Samza application at the end of it can consume from the Kafka topic. So I just want to give a very high-level overview of Flink. Most of you guys might be aware of the Flink architecture here, but I just want to like touch base upon this before we go into the connector side of things, the Brooklin connector side of things. So here, like every Flink job basically has a job manager and a bunch of task manager. So here, this diagram basically uses Yarn as basically a coordination system where a job submission, a Flink program on the left-hand side here could be a Flink SQL application that you'll basically submit to a job manager. And the job manager will basically do execution planning, and it will basically distribute the work across to different available worker, which is the task managers. And the job manager is responsible for ensuring that to ensuring that like the job submission you make is actually successful. It basically sends the statistics back to the client here who's making the submission, and then ensures that all the workers are actually alive. Like, so these workers actually periodically heartbeats into the task manager that the task manager workers basically heartbeat into job manager periodically to ensure that they are alive. And these workers actually have something called as a task slot. So inside a task slot, you can which basically corresponds to a thread in Flink. So you can basically run, let's say, a connector task, let's say, to read data from like a Brooklin or Kafka, etc., or to basically do any kind of processing. And the actor system is responsible for actually doing this heartbeat and statistics. So statistic in the sense like how much memory I'm using, how much CPU I'm using, all these actually statistics to give visibility about the task manager data is actually like sent to the job manager. So this is a high level overview of like very high level of Flink architecture, where you have a job manager and you have like a bunch of task manager. The task manager does the actual work of your stream processing, and job manager is responsible for coordinating these amongst these task manager and taking the job submission and stuff like that. It's a central coordinator. What we want to show here is like in the slide here is like in case of Flink SQL, every stream that we consume here. So as we spoke about before, right? Let's say if you have an Oracle table, you convert that into a Kafka stream through Brooklin that you consume through Flink SQL. So what this means is that in Flink SQL, every stream is converted into a table, basically. Let's say on the left-hand side here, you have an append stream, like which has a different kind of rows. You have insert row, update row, and delete row. So these insert row and update rows are basically like this change log that we have here on the append stream is converted into a change log stream in basically Flink SQL. So you can see here the insert is actually converted into an insert row. Each row actually has a unique opcode. So we interpret this change log and we basically say this particular row insert I1001 Sally is basically insert opcode. Similarly, this update here 10004 Danny is update opcode. So based on this opcode actually carries a special meaning in Flink SQL. So basically, it is used to maintain state. For example, here it maintains a like in this example, it maintains a dynamic table. So basically, as and when you get a row, it basically like kind of like materializes these changes in this example. So we can see here like the most up-to-date change, like after we have a deletion 1004, that row is basically deleted. So this kind of like a special meaning to the opcode enables the Flink SQL operators to basically keep the state consistent. So if Flink SQL didn't do this, the actual application authors, let's say Flink SQL application authors, have to parse these opcode on that side. So this is a plus point with actually Flink SQL. So they convert a stream into a table, and then they do the processing on the table. Once they're done with the processing, they emit the results in the form of a change log downstream. So So for example, here, let's say like we have like a Brooklin event here, which the key is 100. We have like a before event and then we have a after event. So this basically is converted into two rows in actually Flink SQL. So basically, like here in this example, like we have a row. The key is basically the actual key, the primary key of the table, let's say. So in this case, the primary key is basically 100. So before and the fields are basically name and email. So here we have the name is basically John and email is john@aol.com. So and we can see here that after the two fields are basically updated, all the name is basically updated. So this is converted into like two different rows in Active Flink SQL. So these individual rows actually have like a corresponding opcode, like as I spoke before, like update after and update before. And these opcodes are actually like passed on to the downstream Flink operator. So the left-hand side, we have like a Brooklin event, which basically has operation update, and it occurred at a particular timestamp. We convert that into a Flink internal rows, like one Brooklin event gets converted to two rows in case of update. And then this is again passed on downstream to the Flink operator that they can process. This helps actually like the Flink operator to maintain the state, like what is the state to maintain for each stream, the material state that we saw. Sorry, I think I skipped this slide by mistake. So the change capture event basically has, so basically I want to talk about the event format here. So if you have a Brooklin event, it can have, let's say every Brooklin event corresponds to a database or a table operation. That a table operation could be insert, delete, or update. So this table operation is actually encoded as part of the event itself, the event record itself. So as part of the opcode, you will basically have whether a particular event is insert or update or delete. And the key is basically the primary key of the table. Like whatever the primary key, the source table that the user had set, it will contain the actual key that can be used by the stream processing application downstream. And it will contain both the before and after version changes here. So what this means is, in this example, we have like opcode is update. The previous is basically status is inactive, and after the status is active. So by comparing these two, the previous and after, the stream processing application can actually figure out what is the change that has happened on a particular event by just looking at the event itself. So in this case, if I'm authoring a Flink SQL application, I'll be looking at, okay, this particular status is inactive, and after the status is active. So I know that this particular state, this event contains a state from inactive to active. So this is an example of a Brooklin change capture event, and it basically encapsulates all the information which is needed for the streaming application to process. And this conversion here that we do on the connector, it converts this before and after into two independent rows. So basically, like now I want to just give an overview of like the Flink source concept before we go into the actual connector that we basically built at LinkedIn. So the connector that we built at LinkedIn is basically a Brooklin connector, which can consume data from Brooklin streams in Flink SQL application. So before that, this slide talks about the different source concepts. So as we saw on the first slide there, that every Flink application has a job manager and a bunch of task managers, right? So the job manager, so basically in case of like Brooklin connector, there is this component called a split enumerator. So the split enumerator is it's actually it's a component that is responsible for actually like getting the state about the actual stream. Let's say if you have a Brooklin stream, this enumerator is responsible for getting the state of the Brooklin stream, how much partitions are present in the Brooklin stream, and it kind of like assigns split to the task manager. So in this case, let's say like we have 3 task managers, and the split enumerator is responsible for actually figuring out which partition to assign to which task manager to read data from. So the source reader is where the actual reading of event happens from Brooklin, and split enumerator is responsible for actually coordinating amongst the source readers. So this is something that we didn't build. It's a Flink internal concept from after Flip 27. Like this is a new architecture, new IO architecture that Flink supported after Flip 27, where they came up with this model of a split enumerator and a source reader, where the enumerator will actually get the data, all the metadata for a stream, and will take care of distribution, partition distribution across available source readers. And source readers will be actually performing the reading of messages, processing and emitting data downstream. So this also again like a Flip 27 concept, where like it talks in terms of the actual interactions here. So basically, like the job manager and the task manager talks in terms of the RPC gateway here. The RPC here is the Akka RPC gateway, and the split enumerator and the source reader talks in terms of the source event here. The source event is the kind of a contract, like a schema that basically the split enumerator sends to source reader. So in one example, it could be like the source reader could request split from the split enumerator. Let's say when a source reader comes up, it can register itself to the split enumerator and can request a split. It will be sent in form of the source event here. This is the schema on the top. And the split enumerator can actually send that split back to the source reader. One of the nice things about after Flip 27 is that we can come up with a custom instances of source event, and it can actually help us influence the processing that happens, or model our processing for between the split enumerator and source reader. So before the Flip 27, like I think there is no way for us to customize the protocol between the split enumerator and source reader. After that, like after Flip 27 and Flink, we can actually like customize it. We can actually modify it according to our requirements of connectors. This again actually talks in terms of the split as well as like, so basically like as we saw before, right, the split enumerator runs in the job manager. It maintains a separate checkpoint called as enumerator checkpoint, where it stores what are all the splits I have discovered from for a particular stream. Let's say if you have Brooklin stream, it can have like 10 partitions. So the split enumerator can actually maintain a local state saying that, okay, I have discovered 10 partitions. And as and when a reader basically says request split to the enumerator, it can actually assign a particular split to the readers. Let's say in this case, we have one split enumerator and 3 readers. So it's kind of a two-way communication. The reader goes and asks split enumerator for a split, and the enumerator returns back a bunch of split amongst the readers here. So if you have like six partitions, let's say 6 partitions in case of like a Brooklin stream, the split enumerator can assign like 2 splits to each one of these individual readers. And the readers themselves actually maintain their own individual checkpoints here, where like to what offset they have read until a particular in a particular split. Let's say you have partition 0, you can maintain that I've read till like offset like 100. This state is maintained in the reader checkpoint here. Now, giving with all of these contexts, now let's look at the actual interactions that we have with the Brooklin split enumerator, right? So in the bottom, we have this Flink client, which submits a job to the job manager. And we have this Brooklin split enumerator. So it will basically like read the partition metadata from the Brooklin server for a particular like change data stream. So for example, in this case, if it's a member profile stream, the Brooklin data stream client and the Brooklin split enumerator will go and read the partition metadata from the Brooklin server for the member profile stream. And it will figure out, okay, I have like 2 different task managers, 1 and 2. Now it will basically assign the Brooklin partition splits to each of these individual source readers which are running there, and they will be reading the actual messages here. So this Brooklin data stream client, these readers here will be reading the messages from Brooklin. And basically we have a individual system called as lag monitor or burrow in LinkedIn. So it is used to basically like track the progress of individual streaming applications. Let's say if you have a streaming applications and we want to know the progress of the streaming application in a stream. So we keep track of the lag of a streaming application in a system called lag monitor. So as and when we do checkpointing, the checkpointing happens every 1 minute. So this system will be like this Brooklin source reader will checkpoint, okay, for partition 0, I have read till like offset 100 into this lag monitor. This will be used for alerting purposes. Let's say like if some external system wants to figure out if this if the streaming application is lagging or not, or is it progressing enough or not, it will be like creating alerts on this lag monitor. So this is the high level overview of like Brooklin split enumerator. So we have authored a custom split enumerator here for actually building this connector in LinkedIn, and that integrated with the Brooklin server I spoke before in the first slide. And then it basically like, and we also authored our own Brooklin source reader, like source reader and Brooklin checkpoint manager, etc., to basically like manage the checkpoints. At a high level, it's actually similar to the Kafka split enumerator in open source, or Debussy split enumerator. So this is as far as I know, this is another change data capture reader in Flink SQL other than Debussy. It follows the same architecture as Debussy, basically Debussy connector in open source. So here we basically see in terms of like what are all the classes. So basically, like, this is a Flink SQL app, right? So what are all the classes that are involved in different stages of metadata planning and runtime and execution, etc. So the crux of what we spoke about basically runs in the bottom layer here, the runtime, the Brooklin source, Brooklin split enumerator, source seed, all of them basically lies in the runtime. Everything else is basically the metadata layer, which is actually runs on the top. So yeah, what we spoke before actually runs on the IO stack layer, the bottommost layer, the runtime, what we saw in the previous slide. So basically, like these Flink SQL applications with LinkedIn, they basically periodically checkpoint a lag monitor. It's kind of a lag tracking system that we have at LinkedIn, where we can actually figure out which Flink SQL application is progressing till what point when consuming from a stream. And the Flink checkpoints that we have on the individual like nodes in the task manager are actually backed up in GPFS. We actually have smart alerting on the lag. Let's say if you have application that is not progressing enough when consuming data from a Brooklin stream, we basically define alerts. Let's say like if your application is not let's say your lag is greater than a particular threshold. Let's say you are not processing. If your processing rate is less than a particular threshold, will basically generate alerts. So what we want to cover in this section is that like common CDC pipeline patterns that we have in production at LinkedIn. This is not an exhaustive list in terms of what we do in like a managed SQL at LinkedIn. This is some most common patterns that we have. So this section covers all of these patterns like one by one. I will talk through each of these patterns one by one. So here, I think what we have here is on the left-hand side, we have this Espresso table one. Espresso, as we saw before, it's a distributed document store at LinkedIn. And as we see this Brooklin streaming system is basically pulling in the changes. The changes here is the actual update that happens on this table. And then we have a Brooklin change capture stream, which is actually a Kafka topic. So this Brooklin system is basically pulling in the changes from this Espresso document store table, and basically actually puts it into a Kafka topic here, which is the Brooklin change capture stream, which is consumed by a Flink SQL application. Let's say here, it could be like a map. An application could have any logic, right? Map, filtering, or any kind of custom UDF and projection. And we kind of write that state back into a Espresso table, like where we read data from Espresso table, do some kind of massaging through this Brooklin stream, and then we write the data again back into a different kind of Espresso table. One common example could be like, let's say if you have a member profile, the member profile can contain like, let's say 500 or 600 field, and it is stored on Espresso table. But a consumer might be interested to only serve, let's say, maybe interested in 10 fields out of the 500 fields. So they'll be authoring a Flink SQL app, which will be consuming the Brooklin stream corresponding to Espresso table, and will be only selecting the fields that the application wants, and it will write that to Espresso table. That's one common or one very simple example. So here again, like we have a scenario where we want to talk about a scenario where we have like a stream remote table join. So basically here we have an Oracle table on the left-hand side, the orange box, which is like so as usual, Brooklin basically pulls in the bin log from the Oracle table and creates a change capture stream. So we have a Flink SQL application here, which basically like consumes the change capture stream, and it kind of enriches this CDC events by looking at a Couchbase cache, or it could be any external storage here. I just took actually Couchbase cache as an example, but it could be Espresso, it could be MySQL, it could be any external storage layer that we will be like querying. Let's say like from this particular event, we are looking at a field, we'll be querying Couchbase cache, get the data for the particular event, and maybe like massage the data and emit the results downstream. So here, this is the Kafka topic. We kind of like get the so for every incoming change capture event which is coming from this Kafka topic, query the Couchbase cache or any kind of a remote store. This is called like a stream table join, because you kind of join based on the key. We basically like enrich these events and do some massaging, and then emit the result to a Kafka topic, which downstream systems can consume. This is actually like similar as before, but rather than like no state here, we have a state here. State managed on a Couchbase. The state could be any external storage, like Espresso, MySQL, or anything. So this is a common pattern, which is like a stream remote table join. Another aspect here is like apart from like querying store directly. So in this pattern, like similarly, like we have a like a source of truth table, which is Oracle table 1, which contains some kind of a like entity, like profile or member profile or like jobs or any entity, like or a page, LinkedIn page, product page. So you basically have an entity which is like present in the source of truth. And we consume the changes here is the bin log again, like the bin log from this table, and then we create a change capture stream. The Flink SQL application will be like for every event, it will go and query based on some fields that are present in the event. You will basically make a REST API call to a remote REST service or a remote HTTP service or a remote RPC service. It will get the data back and massage it, and will do some processing internally, and then will emit the data to a Kafka topic. So where the common pattern here is like you query a REST service on every event, and then you do some massaging, and then you emit the state to a different stream. So
Hi, Santosh. I just want to barge in here in the interest of time. So about 5 minutes left, and there's some.
Okay. Sorry about that.
Wrap it up. Yeah. Thank you.
So here we have this scenario of like a change capture joins where the Flink SQL application consumes a change capture stream from 2 different Brooklin streams, and it kind of does a join based on some condition, some kind of like a condition based on the events present in coming from these 2 streams, and then it kind of emits the results to a Kafka topic. In the interest of time, I'm not explaining further. I'm skipping the slides. The stateless transformers here basically like where we consume the event, and then we apply some processing, and then we emit to a Brooklin state itself back, a Brooklin sync itself back. So the difference here is the events are emitted in the form of a change capture model. I think I have a few more slides. Let me rush through this. In the use cases section, I want to just talk about common use cases of using the Brooklin CDC connector at LinkedIn. So we will look at a couple of use cases. So here, I think, so here like, so this is a real search index maintenance job, which is basically based out on Flink SQL. So on the left-hand side, we have a DB table here, DB table 1, DB table 2, and the Brooklin stream 1, stream 2 we consume. We can actually create a Brooklin stream 1, stream 2 based on this table, and then we consume it on a join job using the previous pattern. And it is enriched using the Couchbase cache. The results are emitted to a Brooklin stream 4, like so where like it is actually taken by a search indexer. There will be a search indexer, which is a streaming processor, which will be consuming these updates and will be updating the index, the search index. So here again, we have like a Brooklin stream from a database table, and we basically make a REST call as in the previous pattern, and then we emit the enriched result, some kind of massaging we do, and then we enrich the data, and then we emit the result to the Brooklin stream 5. This again is going to update the index. Just quickly moving on. So here again, Espresso Couchbase caching here is like a typical example of a Brooklin use case with Flink SQL. So we consume the change capture stream from an Espresso table, and on every event we go and update a Couchbase cache. So like this is a way of like repopulating a cache based on a change that is happening on an Espresso source of truth. So we kind of like build this cache on the side. We kind of like warm up the cache based on the state which is present on a source of truth table here, Espresso. And then once the cache is fully warmed up, it will be like served for online queries. So the notion here is you get the changes happening on a DB, and then you have streaming processor which can actually populate the Couchbase cache asynchronously. So the cache will be eventually consistent with the Espresso documents. I think I'll briefly talk about this. In the interest of time, I'll quickly go over the lessons we learned. So we wanted to support schema evolution in our pipelines. So if any of our downstream schemas changes, we make upstream schema changes, we want to ensure that like we have strict rules enforcing like stopping backward incompatible schema changes in our pipeline. And we want to actually have a stronger backfill support, like reprocessing even from an earlier point in time from pipeline. It's a very common use case. We wanted to actually have a stronger support for it. And we wanted to add like runtime validations in order to like track and like audit consumers, and invest in like local testability, like so that like it's easy for people to author applications and test it. I think that's all I had.
Okay. Could you go through the Q&A questions?
Yeah. Okay, so there is a question from William. So he's asking about how do you compare Brooklin with Debezium? So basically, Brooklin and Debezium are two different sort of systems. I think both supports the change data capture form of consumption from a source of truth. Brooklin is like open source and Debezium as well. So I think both of these systems were developed at the same time. It's not like one system was authored before it. And in terms of like, as far as I know, in terms of like functionalities, they're functionally equivalent of each other. One of the benefits about Brooklin is not tied to Kafka alone. Let's say like you can have a Brooklin system consumed from AWS Kinesis or Azure Event Hubs, or it's not tied to a particular streaming PubSub system. As far as I know, Debezium is tied to Kafka, if I'm not wrong. Second question is Andy Mao. Does Brooklin listen on changes by listen on some Kafka topic, Espresso/Oracle send the CDC data to? So I think the way Brooklin actually gets the changes is basically like from the actual DB source itself. So like in case of like Oracle, it basically supports a bin log. You can pipe the bin log. So if you are aware of MySQL, it basically supports a particular bin log. And then you get the bin log, and then we write the data into a Kafka stream. So these are not actually like, it doesn't have a Kafka topic in between. There's a question from Swati. Will there be exactly once consistency in this case? How is the data loss handled in Brooklin? So I think there is, so basically Brooklin supports at least once consistency. It doesn't support exactly once. There is no concept of data loss here, right? So if we don't skip any events, we keep track of like, we have like external systems which monitor Brooklin to ensure that there is no data which is being missed. So we have like systems like Kafka Audit, and which kind of like tracks whether if there are any event that Brooklin is supposed to process, it's missed. So we have like external audit system which figures out if Brooklin is missing processing events or not. So Brooklin supports at least once processing, and there are external monitoring tools which takes care of data loss scenarios. Never occurred to me to use a CDC system. Okay, neat, thanks. What is the initial point of learning to reach this level of knowledge? I'm not sure how to answer this question. What is the initial point of learning to reach this level of knowledge? I don't know, like I think there's the Flink open source community is very helpful. So we can actually send an email to Flink dev or like a Flink users, so they'll be responsive. And I had like good mentors at LinkedIn, like they all were like very helpful in helping me learn. So that's how. Yeah. So
there's one more question.
Yeah, each event stream can belong to only one table. Yes, that's right. So I think in case of Brooklin, like each stream to table, there's one-to-one mapping. That's right. How it ensures to process event on time basis? Is it process event sequentially? There's a question from Naren. How it ensures to process events on time based? Is it process event sequentially as we update the data in source DB? That the events are not processed on Brooklin on time base. It's actually processed sequentially, basically, as we update on the source DB. So in case of, let's say, for example, MySQL, whenever you update a MySQL table, it has a corresponding thing called as bin log. You kind of pipe the bin log into a Kafka topic. In essence, that's what we're doing. Like you kind of pipe the bin log into a Kafka topic, which you mirror it down. That's actually it, I think.
Yeah, I think those are all the questions. Thank you very much, Santosh. I think this concludes all the topics for the meetup this evening. Thank you for your participation. I think one last message is this forum is an open forum. So if you have any topics you would like to share with the community, please reach out to me, DJ, and FA on LinkedIn. Thank you. Have a
Thanks,
good evening.
everyone.
Bye.
Thank you.